Welcome back, class. Today, let's look at the electron microscope. This instrument allows scientists to view structures that are far beyond the reach of traditional light microscopes. Let's find out how it works, its advantages, limitations, and the different types available. Unlike light microscopes that use light waves, electron microscopes use a beam of electrons to illuminate specimens. These are tiny, negatively charged particles that orbit atomic nuclei and can behave like waves under certain conditions. What makes electron microscopes special is their ability to focus these electron beams using electromagnets, achieving extremely short wavelengths, much shorter than visible light. This allows for much greater resolution. Let's clarify two important terms. Resolution is the ability to distinguish two closely spaced points as separate. Magnification refers to how much larger the image appears compared to the actual object. Electron microscopes can reach magnifications of up to 250,000x, far surpassing light microscopes. However, keep in mind, increasing magnification doesn't improve resolution unless the resolving power is sufficient. Here we can see the structural layout of two types of electron microscopes. Transmission electron microscope, TEM, electrons pass through the specimen. Scanning electron microscope, SEM, electrons scan the surface of the specimen. Both types use electron beams, electromagnetic lenses, and vacuum systems, but produce different kinds of images, which we'll discuss soon. The electron microscope has two major advantages. It offers high resolution, up to 0.5 nanometers, which allows us to see incredibly small structures like organelles, viruses, and macromolecules. It can magnify extremely tiny objects, revealing details invisible to light microscopes. However, there are some drawbacks to keep in mind. Specimens must be viewed in a vacuum, meaning they must be dead. Delicate preparation can alter structure due to staining or dehydration. They are expensive to purchase and operate. Preparation is time-consuming and requires trained professionals, and specimens often degrade under the electron beam, so images must be taken quickly. Let's now compare light and electron microscopes. Despite their differences, they share some similarities. Both are used to magnify specimens. Both use lenses and a stage to hold and manipulate samples. They both aim to illuminate and resolve fine details, although using different methods. Now for the key differences. Light microscopes use light, produce color images, and are ideal for observing living specimens in real time. They're portable and relatively affordable. Electron microscopes, on the other hand, use electrons, provide black and white, highly detailed images, and require vacuum conditions, meaning the specimen is dead. They are also more sensitive to magnetic fields. There are two main types of electron microscopes. SEM, scanning electron microscope. It scans the surface of the sample and produces a 3D-like image. TEM, transmission electron microscope. Electrons pass through the sample, producing highly detailed images of internal structures. Think of SEM for surface structures and TEM for internal architecture. Let's now look closer at the scanning electron microscope. It excels at showing surface structures and gives a 3D impression. It allows for larger samples to be viewed compared to TEM. However, its resolution, 0.2 mm, is not as high as TEM's, 0.5 mm. So SEM is great when you want to explore surface textures, like the outer shell of pollen grains or the skin of an insect. Conclusion. In summary, the electron microscope has revolutionized biology by revealing structures invisible to the naked eye. From virus particles to intracellular organelles, its contribution is unmatched. However, we must also understand its limitations, expense, complexity, and the inability to view live specimens. Up next, We'll work on comparing micrographs from light and electron microscopes, and you'll learn how